So Mathematica has the ability to minimize functions or find minima using a find minimum. And indeed it can minimize functions of several variables, or in fact many variables. And that capability can be used to solve a quite interesting class of problems that in general are all about finding an optimum shape of something. So let me give a specific example of that. Suppose that you had some kind of smooth topography, some smooth landscape. Think about a hill made of something slick. And then you have a long chain made of beads that are frictionless, attached by springs. And it's a long chain, it's got many beads in it. I'm only drawing a few of them. And now what you want to do is you want to drape that chain over this hill and find out what the optimum shape, where do the beads want to go. So you have a lot of beads, so a bunch of them are going to be piled up over here, and then there'll be a certain number of them that cross over the hill, and then there's going to be a big pile of them that pile up over here because you have a lot of extras. And so there's some potential energy function, call it u of phi. Phi is going to be the sort of x-coordinate here, and that's, I'm going to assume for purposes of this problem, minus cos phi, and so that means that this potential energy surface here is minus 1 at phi equals 0, and also at phi equals 2 pi, and it's plus 1 at phi equals pi at the center. Okay, and so the optimum involves, how many beads get across the hill, how quickly. If you take very few beads to cross the hill, well then not very many of them are in the unfavorable part of the potential, but the springs are stretched a lot, and that costs you potential energy of the springs. So the problem really in finding the optimum shape, in other words the optimum arrangement of these beads as they go across here, is to minimize the potential energy of the problem, which is a sum of two things. So the total potential energy is going to be the sum of the hill potential, if you want, of all of the beads, plus a spring term, which I'm going to write as the sum of the squares of the differences between these phi values. And that would make sense, for example, if these were real springs and this hill wasn't very tall, but gravity was large, so that the stretch of the spring is basically given by the difference in the phi and doesn't have anything to do with how high up you are. And then there are other models, other physical situations that lead to a problem like this. The point is, though, that we want to now find the minimum of u with respect to the entire set of phi sub I. And as in any kind of minimization problem, and the more so when you have many variables, you need a good initial guess, which is going to be motivated by this picture that the sort of solutions you might expect are going to look like this. That is, there's a bunch of beads on the left, and there's a bunch of beads on the right, and there's a certain, those are at 2 pi and these are at 0, and there's a certain number of them that it takes to cross over, and then how narrowly or how quickly or slowly this crosses over is going to be in effect the thing that gets minimized over. So now we're going to illustrate how we go about solving that problem in Mathematica. So the first thing we need is the potential function, which I've just said I want to have the minus cosine phi for no particular reason. And then we need the total energy function, which will depend on the number of particles and of course all the phi values of the particles. And you'll see that we store those in a slightly funny way in this problem. I'll explain that in a little bit. There's two pieces to the potential energy, as I said. There's the sum of the potential energy of the hill for each particle. That's this first term I've just typed. And then the second term, and we're just going to assume a spring constant of 1 here. The second term is the sum of the squares of the differences of the adjacent phi values. And that sum runs from I equals 1 only to n minus 1 because the last because we're taking the difference between the I plus first and the ith bead, and there's n beads altogether. Now, to construct a model initial solution, we're motivated to construct a sort of tanh-looking curve, and exactly what that should be takes a little bit of experimenting, but here's something that makes sense. It turns out that if you take pi times 1 plus tanh of some number times x minus a half, that runs between 0 and 2 pi, crosses over in the middle at x around a half, and how fast it crosses over has to do with what number you put here in this width position. So based on that, we define an initial solution, which is a function of the width and the number of beads, which is going to be a table of values that will be used for the different bead positions. And as I say, this is going to be an initial guess, which will adjust. And instead of x, what we write is k minus 1 over n minus 1, because k runs from 1 to n, and therefore k minus 1 over n minus 1 will run from 0 to 1. So this is the form of the initial guess function. And we can check to make sure that that does the right thing by just plotting an example for 128 beads, and it does the right thing. Okay, now we need a way of actually evaluating the energy, and this comes back to this business of where are we storing those values anyway. They're not stored in a list, they're stored in a function. They're stored in the function phi. So in order to evaluate, and you'll see why that is in a little bit later, it's a somewhat subtle point. So to evaluate the energy, we have a function called eval e, and it depends on a list of values, meaning the phi values for all the different beads, and so what we need to do is to define the function phi to have the values at the integers which the list tells it should have. And that's done like this. We don't have to know what n is here, just the length of the vowels will tell us how far out to run this table, and you see the table, all that it does is it makes the assignment of the ith value of a vowels array as the ith value of the function phi. And then, having done that, then we just call e total with the n, which is the length of the vowels. And actually I could have done it like this, now that I think about it, making myself a little internal variable n, like that. Okay, so for example, I can evaluate the energy of the initial solution with the width parameter 120, and I get some value. And furthermore, I can evaluate a variety of width values and list plot them in the following way. So here's a table of pairs of W and the corresponding energy value, and I'll do this for, I don't know, W values from 5 to 200 in steps of 5, just to get an idea of where the minimum is. And so you can see, oh yeah, there's a minimum there for a width of about, I don't know, 60, 70, 80, something like that. But we'd like to know more precisely than that, so we'd like to use find minimum to find the best possible width. I can begin to set up the bookkeeping for doing find minimum with a whole lot of variables in the following sort of way. I say, okay, the variables that I want are going to be a table of phi sub I from I, well, I don't want to touch the end ones because I know that they sit at the bottom of the well. And so I will, well, let's start off saying that the number of points we want is the length of the values, which will be the initial condition. Right now, let's just say that's 128. And then the list vars will be the list of variables that will be the ones that find minimum minimizes over. And then the other thing that you have to give find minimum is a list of the initial values for those. And so together that forms what's called the variable specification, or what I'm calling the variable specification. So the table is a list of the variables and then the initial values that go with them, like that. And now what I want to do is to make sure that phi of 1 is always going to be the left-hand boundary, which will be 0, and phi of 128 will always be the right-hand boundary, which is 2 pi. I think I've got everything that I need, except that I'd have to have the initial values as vals. Okay, so that was what I called them. So vals should be the initial solution at whatever I decide my initial guess is going to be, like so. And now I can do my find minimum. I hope this works. Apparently not. So what I need is that the values of phi are not yet defined when they get passed to the find minimum function. So I'm going to put this clear phi statement in here because phi got set up there. And now let's try it. Okay, so then I get a big long list of substitution rules. So what the heck was going on here? Let's look at what varspec is at the end of this. Okay, so I made my values vals from the initial solution, and it's a big long list of these points which I was plotting up here someplace, like that. And then I say there's 128 points. I clear my function phi. I declare my the variable specification as being a big long list of phi as yet undefined and what its initial value will be. And so then these things, phi 2, phi 3, phi 4, etc., are perfectly acceptable variables for find minimum to minimize with respect to. Okay, because what find minimum wants is a function and a list of values which it's supposed to minimize with respect to, and initial values for each one of those. And you see that it wants a list there of pairs, variable, value, etc., like that. Well, if you've got a great big long list of possible variables, it's awkward to generate a whole bunch of names for them. And so that's why the trick of using phi as a function of I with respect to which we're minimizing, that's why that was used here. But you have to make sure that those variables don't have a definition before you pass it to the find minimum, which is why they needed to be cleared before you go in. So that's a little bit complicated, but that's how you deal with lots of variables handed to a function like find minimum, or indeed a function like ND-solve. You can often find yourself in situations where you have some large number of differential equations to solve, and you need to give them all names, the variables all names, and a scheme like this is a good scheme. Okay. So that's how you get your answer. You see this is the minimum value right there, and the answer we want in a certain sense is this big long list of substitution rules. So if we want the final values, then that would be a list of the phi's as substituted by that. So I might do it like this. Take the variables vars and substitute them by the answer, the second part of which was the list of substitution rules. And that just gives me a big long list of values, and I can list plot those. Okay, and then I can compare it to let's see, let me give this a name. I can compare it to a list plot of the initial solution with different widths. You remember that the initial solution of 120 of a width of 20 was what we guessed initially, and that, of course, wasn't very close. But what we saw from the minimization above was that actually the width wants to be about 80, and so if we put that parameter in there, then indeed they are quite close. Okay, so to recap, what we've done here is minimized a function of many variables, in fact a list of variables indexed by I, using this trick of defining a bunch of variables in terms of the function phi, but not having a definition, and just putting an I in there so that we'll have a big long list of variables to minimize over.